Alright, I know this is a re-upload and I know it's cheap, but two things. First of all, I was wrong in my initial video, and this is why it's a re-upload, and I need to put this editor's note before the start, is that, we are not harvesting the electron volts as pure electricity, no. The electron volts represents the heat that's going into the water, and then boils steam, and then that turns the turbine, which activates the generator. Alright, that is how the power is produced. I'm sorry for that mix-up. Alright, and the second thing, I will be making another video very soon about radiation, so stay tuned for that. Alright, into the video.
Oh my god, you said that you would upload once a week. Are you lying? Yeah, you're making empty promise.
Shush.
What is nuclear power? How does it work? And isn't it really, really dangerous? I'll be exploring these questions and more in this three-part series where I'll be covering three methods of nuclear power: nuclear fusion, nuclear fission, and nuclear decay. In this episode, we'll be covering my personal favourite, nuclear fusion. Nuclear fusion, unlike its opposite nuclear fission, uses very light elements no larger than iron, which are usually found in abundance in the cores of stars, the only place where natural fusion occurs, and it has virtually no waste at all. But to understand the basics of nuclear fusion, we first have to understand the basics of atoms and isotopes. An atom is the basic building block for almost all matter in the universe, and it is made up of three subatomic particles: a proton, a neutron, which is important later, and an electron. The protons and neutrons form the nucleus, and the electrons stay in orbitals. Atoms are categorized into different groups, elements, by the number of protons they have. This is known as the atomic number. The number of protons will always equal the number of electrons in an atom, and if it doesn't, it is now classed as an ion, but that's a topic for another video. As I mentioned earlier, neutrons are important, and that's because they determine what isotope any element is. Isotopes are members of the same element but with different numbers of neutrons. And the number of neutrons is important for another reason, because if an atom has too few or too many neutrons, it becomes unstable and subsequently radioactive. Now that we have a basic understanding of atoms and isotopes, we can get into nuclear fusion. The current idea of nuclear fusion is to take two specific isotopes of hydrogen, deuterium and tritium, and to squeeze them together hard enough to make them fuse. But they really don't like being near each other, so they have to be very hot to get the fusion going, like millions of degrees hot. And so far, the most promising method of doing this is called magnetic confinement, basically using giant electromagnets cooled roughly to negative 270 degrees Celsius to squeeze the atoms close enough for fusion to happen. When fusion does happen, the extremely hot nuclei bash into each other and merge, creating three things in the process: a helium-4 nucleus, a free neutron, and roughly 17.6 mega-electron volts. It is the electron volts that we are trying to harvest. But what about the other products? Surely if it's a nuclear reaction, the stuff that isn't the electricity must be dangerous. It is a nuclear reaction after all. Well, no, not exactly. The helium produced is not radioactive, and the spare neutron eventually decays into a hydrogen nucleus, which usually takes about 10 minutes. And thus nothing that comes out of the reaction is radioactive waste or unuseful. The helium and hydrogen byproducts can be used for other purposes, and the electricity is, well, electricity. And even though this sounds pretty good, in reality it is extremely difficult to achieve the desired result, often producing less energy than is used in the fusion process. And despite how many advancements have been made, especially if you've seen the news recently, fusion energy has never been able to produce more energy than it takes to run the reaction, until very recently, and thus the phrase, fusion energy is always 20 years away, was born. This is basically the end of the video, but if you want to know more about nuclear fusion, such as the requirements of fusion or other methods, I highly recommend checking out the Wikipedia page in the description below. Anyways, I'll see you in the next video where I'll be covering radiation. See ya!